Okay, so in photosynthesis, plants make glucose, C6H12O6, and oxygen from carbon dioxide and water. Write a balanced chemical equation. All right, so the first thing you're going to have to do is understand which one are the products and which one are the reactants. All right, so if plants make glucose and oxygen, those are going to be the products. From carbon dioxide and water, those are clearly the reactants. So I'm just going to do this in red. So carbon dioxide, CO2, plus H2O, those are the reactants, makes C6H12O6 plus O2. Now, I didn't ask for phases, so you don't need to do phases in this. That's fine. So this is the first step, is I'm writing a skeletal equation. And you'll notice too that I'm writing these little lines in front of my compounds. That's to make sure that I leave enough room for myself for the coefficients. I suggest doing the skeleton equation with the little lines in pen, and then writing and messing with your coefficients in pencil, because you're going to be making lots of mistakes, especially while you're getting used to this. I mean, I still make mistakes when I balance. It just happens. All right, so now that we have the correct chemical equations, right, CO2, the only thing that's tricky about this, it says and oxygen, so always remember oxygen's a diatomic, and especially in chemical reactions, if it's by itself, it's always going to be O2. So what we're going to do is we're going to start comparing products and reactants for each element. We're going to start with carbon. On the reactant side, we have 1 carbon, but on the product side, we have 6. So we're going to have to put just easily a 6 right here to go ahead and balance out the carbons. So I like to do a little check mark. Just be like, okay, my carbons are now balanced. Now I'll move over to oxygen. All right. Actually, I'm going to skip oxygen because I have 3 oxygen on, no, I have, oxygen gets a little bit more complicated. So let me see if I can do hydrogen first. Hydrogen on the reactant side, I have 2. It's also, why did I switch to hydrogen first? Well, because oxygen is spread out over 2 compounds, I kind of like to balance that, and hydrogen is only in 1 compound here and in 1 compound here. Just, it's going to be easier to balance that way. So sometimes if you get stuck in between, well, what should I balance, oxygen or hydrogen first? Do what I just did and pick the element. If there is one element that exists only in 1 compound, use that one first. So here I have, on the product side, the reactant side, I have 2 hydrogen. I don't know who that is. I don't know why. I have do not disturb up, but it's just showing up. Okay, so 2 hydrogen here, and I have 12 hydrogen on the product side. So what am I going to have to do? I'm going to have to put a 6 here. So now I have 12 hydrogen. So hydrogen's now good. Okay, cool. Now, what's left are my oxygens. All right, so I have quite a few now on the reactant side. I have, from CO2, I have 12 oxygens, right? Because there's 2, and there's 2 per CO2 molecule, and there are 6 of them, so 12. And I have 6 oxygens from water, so a total of 18 oxygens. On the product side, I only have 2. So this is going to be pretty simple, right? I can easily make this a multiple. I can just divide 18 by 2, put a 9 here, and now I have 18 oxygens. Whoops, no, I screwed up. Sorry, my bad. Hold on. See, this happens. You're going to have to do that. I forgot about the O6. All right, so we have 6 oxygen plus 2 oxygen for a total of 8 oxygen, and we need 10 more. All right, I don't necessarily want to mess with the coefficient in front of glucose because I already have my carbons and hydrogens balanced. So I can easily, right, let's go ahead and mess with this guy with the coefficient in front of O2. So if I have 6 oxygens and I need 18, so I have 6 oxygens here, I don't want to mess with this anymore. So I want to use this 6 right here. So, and I need 18 total. So I'm going to need to have this, right? This one, I'm going to have to make up for 12 oxygens, all right? Because the 6 are already right here. So all I need to do is just make this guy give me 12 oxygens. So I'm just going to put a 6 right here. And now we'll look back and we'll sit back and say, okay, well, how many oxygens do I now have? I have 6 plus 12 equals 18O. Put a little check mark here, 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 and here. All right? So it looks like the whole thing is balanced. Let's do another one. Write a balanced chemical equation for the reaction between solid silicon dioxide and solid carbon dioxide, or sorry, solid carbon, to produce solid silicon, monocarbide, and carbon monoxide. Okay, so let's take a look at what is all we have to go back to chapter 9. We also have to understand the phases, and we're going to have to write a really nice skeleton reaction. So it says for the reaction between solid silicon dioxide, all right, so silicon dioxide, SiO2, I'm going to include the phases in here because the phases were given to me, plus I'm going to leave a space, right, for my coefficient, solid carbon. So I'm just going to put C, S, to produce, right, to produce, oops, that's your arrow, silicon monocarbide, oops, sorry, that is correct, I just want to make sure that I have enough room for my coefficient, and it's a solid, plus carbon monoxide gas. So again, a line, so you have plenty of room for your coefficients. Carbon monoxide gas. All right, so that is the skeleton equation. Now we're going to have to go through and we're going to have to balance the whole thing. So again, we're going to start on the left-hand side of the equation. And we are going to go to silicon. Silicon here we have 1 silicon in the reactant side, or reactant side, and we have 1 silicon on the product side. So I guess we can go ahead and say for right now, silicon is good. Now we're going to move over to, should we skip oxygen? Well, actually, let's go ahead and skip oxygen. Let's go to carbon because I like to balance oxygen, hydrogen last. So let's go to carbon. Here we have 1 carbon atom, and here in the product side we have 2, right? We have 1 here and we have 1 here. So we're going to have to put a 2 here. So now I have carbons are balanced. Now let's go back to my oxygen. Oxygen on the reactant side are 2. So I'm just going to go ahead and so you can see 2O. But on the product side, we only have 1. So we're going to have to put a 2, right, in front of here, in front of the carbon monoxide in order to get out 2 oxygen. So now we have 2 oxygen and 2 oxygen, so we're good, but here's the problem. I screwed up my carbon. Oops. Carbon is now out of balance. So now I'm going to have to go back and fix my carbons. How many carbons do I have? I still have 2 on the reactant side, but now I have 3 carbons on the product side. So all I'm going to need to do is go back and just easily change this from a 2 to a 3. So let's go through and make sure that we have everything correct. Always go back and check your work. All right, so for silicon, we have one silicon here, and we have one silicon here. So silicon is good. All right, oxygen, reactant side. We have 2 oxygen on the reactant side, and we have 2 oxygen on the product side. So we're good and good. Now carbon, we have 3 carbon on the reactant side, and we have 3 carbon on the right. Check, check. All right, so that is completely balanced. All right, the common multiple approach. So here's an example. Potassium chlorate decomposes into potassium chloride and oxygen. I didn't give phases, so you don't have to write phases down, but you do have to write the correct skeleton equation. So we have potassium chlorate, KCl chlorate O3. Now it decomposes, all right? So since it decomposes, it doesn't react with anything. It just decomposes into something else. And what does it decompose into? It decomposes into potassium chloride. If you look at the periodic table, potassium is always a +1. So again, it's still going to be KCl plus oxygen, right? O2. Right? Remember, oxygen's a diatomic, and in chemical reactions, we always represent it as such. Now we're going to go through and we're going to balance it. All right, so if we start on potassium, we have 1 potassium here, cool, and we have 1 potassium here, so we're good for potassiums. Chlorine, we have 1 chlorine on the reactant side and 1 chlorine on the product side, so we're good. Now we have 3 oxygens on the reactant side and only 2 oxygens on the product side. So we're going to have to find some kind of common multiple. It's really the lowest common denominator, right, between 2 and 3, which is 6. So we're going to have to say, all right, well, if I'm going to multiply this by 2, I'm going to have 6 oxygen, right? So I'm going to put a 2 here. And if I multiply this by 3, right, I'll have 6 oxygen. So I'm going to put a 3 here. So now that I have 6 oxygen on the right or left and 6 oxygen on the right, go ahead and do a little check mark. But now I have to go back and double check everything. Going back to the potassiums, my potassiums are out of whack. Now I have 2 potassiums here. So I'm going to have to put a 2 here. Right, so now my potassiums are good. And chlorine, same for the chlorine. Right, now I have 2 chlorine, and now I also have 2 chlorine. So I actually don't have to do anything else. All right. So chlorine is now good. So the common multiple approach again is what you just need to do is find the lowest common denominator. Here again I started off with 3 oxygens, and on the product side I started off with 2, and the lowest common multiple, right, to get to the lowest common denominator, which is 6. So I multiplied the 3 oxygens that I had by 2 to get to 6 oxygens, so I put the 2 here, and I multiplied the 2 oxygens that I had here by 3 to get to 6 oxygen, and I put the 3 here. Then I went back and double checked everything to make sure that it's all correct. And turns out that it is, and it's completely balanced. And this is just a slide telling you about everything. So it takes you through the whole thing, blah, 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 blah. Oh, and I didn't end up balancing it at the end, so let's go ahead and just, what did we say it was? It was, because it's a total of 6. So we're going to 2, 2, and 3. There you go. All right, just double check and make sure that's right. Because clearly my 2, 2, and 3, My short-term memory is not so great right now. Okay. So, I just went over several examples on how to balance chemical equations. Again, what you're going to have to do is always write a correct skeleton formula. Leave room for coefficients. Make sure to include, here, I'm going to go ahead and do this really fast. I'm going to, nope. Sorry, I'm going to add a page, and I'm going to tell you exactly so again, correct skeleton equation, all right, and that means correct formulas, and correct products, reactants, all right? If phases are, I should say listed, that's fine. I should say phases are given. If phases are given, you must include them. And then 3 finally, and then you're going to balance that's coefficients only. Okay? So again, you have to always start off with the correct skeleton equation. All right, make sure, oops. Sorry, this is a little messy. Make sure you leave room for coefficients. Okay, so make sure you leave room for coefficients. That way you have plenty of space. And then you're going to, so write the correct skeleton equation that includes correct formulas and identifying the correct products and reactants. And then make sure you leave room for the coefficients. If the phases are given, you must include them. And then you're going to balance using coefficients only, right? Because we talked about you cannot, you cannot change, you are not allowed to change the chemical formulas or the subscripts. Okay. All right, so moving forward, we already talked about balancing. Now I'm just going to wrap this section of the lecture up with aqueous solutions. All right, so it's important for you to understand what an aqueous solution is, and an aqueous solution is something where something dissolves in water. All right, sodium chloride solution, right, is represented NaCl subscript AQ. That when we see NaCl subscript AQ, we have to think sodium chloride in water. All right. So what happens when sodium chloride is in water? Well, if we have, I'll just do it what is this? So in normal life, if we have a sodium cation, right, this is represented by that purple dot, and then we have and let me just do this, and we have a chloride anion, right, that's represented by the green dot, and it is sitting out right on the table like table salt. It's solid. All right, but then when we put it in water, this breaks up, right? The electrostatic interaction that holds the cations and anions together are broken up, I should say, right? they're dissolved. All right, so basically what happens is water breaks that electrostatic interaction and separates the chloride anions from the sodium cations. All right, so what ends up happening is that our solid sodium chloride that was here is dissolved in water. That's what dissolving is, and it becomes NaCl subscript AQ. All right, and in solution, there's none of this. There's no sodium cation bound to a chloride anion in water. It's completely separate, and it consists of independent sodium cations and independent chloride anions. So this is, it only consists of dissolved ions. All right. Substances such as NaCl that completely dissociate, right? That's a really important thing, meaning that if we have, let's see, 1, 2, 3, 4, 5, 6, so essentially there were 6 NaCl formula units, right, that were put into this water solution, and now we have, so we'll say 6 NaCl, and then what ended up happening is that these guys dissociated completely to form 6 sodium cations dissolved in water plus 6 chloride anions. Okay, I didn't write the AQ out here, but I just need you to see that it completely breaks up. All right, and we call this completely dissociating, right? Where all 6 of them break up. All right, that's not always the case. There are some salts that don't completely dissociate, right? Like if you put 6 of them in water, maybe 1 of them out of the 6 will break up. So that's the difference between completely dissociating and not completely dissociating. But regardless, when something completely dissociates in water, we call this a strong electrolyte. All right, it's a strong electrolyte because it dissociates completely into ions. Silver nitrate, in contrast, does not dissociate. All right, it does not dissociate completely. Oh, I'm sorry, I apologize. It does dissociate completely. Like I said, today's not my day. Silver nitrate does dissociate completely. And again, if we were to have it, so this looks like there's 3, right? So if we have 3 AgNO3, when we put it in water, right? I'm showing this kind of like a chemical reaction, but it's really more of a story, like it's a before and after. Right, so then it ends up breaking up into, and this is actually what I'm going to do, is I'll put this up here, because that's what's represented in this slide, right? So we have 3 AgNO3, and then what will happen is we end up having, in solution, 3 Ag plus 3 NO3 minus. Now, where did I get this 3 from? It's just because there are 3 in here. 1, 2, 3. So I just pull it from this. It's not like an actual chemical reaction. I'm just showing you that you have a salt, all right? It's silver nitrate, but then when you make a silver nitrate solution, such as AgNO3, subscript AQ, it dissociates completely. There's no remaining AgNO3 units. They all break apart. So only dissolved silver ions and nitrate ions are present. Again, this is also because it dissociates completely. It is a strong electrolyte. When compounds containing polyatomic ions such as nitrate dissolve, the polyatomic ion stays intact. So that's another really important thing, all right? It stays intact. So even though the silver breaks up with the nitrate anion, right, these guys stay together, right? Nitrogen doesn't break apart from oxygen, right? So that these ions stay together. So what does it mean to be a strong electrolyte? And I'm just going to breeze through this just for time, in the sense of, it's teaching online is pretty difficult. So what does a strong electrolyte mean? Strong electrolytes conduct electricity. Okay, so if you look on right here, we have a battery, we have a light, and we have water, all right, and we have electrodes down here. And essentially, when we try to pass a current through this to light up the bulb, right, basically we need to get a current to light this bulb up. Since there are no ions in pure water, like deionized water, current doesn't flow. But because in strong electrolytes, right, such as sodium chloride, that dissociate completely, right, because they dissociate completely when we drop sodium chloride in water, that allows a current to flow. And why does it flow? Why does current flow? It's just because you have charged particles that are completely dissociated from each other, and they can freely move within solution, right? And because they can freely move within solution, they can then conduct electricity. So the current can flow from the cathode to the anode, I think is what it is, and then goes from the battery back to the light. These, again, take-home message: you don't have to know about cathodes and anodes. You don't have to know about electricity. It's just important maybe to know that electrical current is the movement of charge, but long story short, strong electrolytes conduct electricity. So if you fully dissociate, you conduct electricity in water. Not all ionic compounds dissolve in water. Silver chloride does not dissolve in water. So if you take a hunk of silver chloride and you throw it in water, look what happens. It stays together completely. It remains as a solid. So if you were to put the cathodes and the anodes in solution and to see if the light would start blinking or light up, if this is DI water, no charge is going to go through. No current is going to flow because these ions do not separate from each other. So when silver chloride is added to water, it remains as solid silver chloride and does not dissolve into independent ions. So it does not conduct electricity. It's important for you to understand the rules of solubility. You don't have to memorize any of these things. There's a table that you'll have to understand and that you'll have to read. So a compound is soluble in a particular liquid if it dissolves in that liquid. A compound is insoluble if it does not dissolve in the liquid. Pretty straightforward. For ionic compounds, empirical rules of solubility have been deduced from observations of many compounds. And this is the chart, all right? All right here. This is the solubility chart. So how are you going to read a solubility chart? Remember, we're talking about aqueous solutions first of all. So we're talking about whether or not a compound, most of these, actually all of these compounds are ionic. All of them are ionic. They consist of a metal and a nonmetal. And do these break up or dissociate in water? Are they soluble? So these are just examples that I have. All right, so let's just go through each one of these and look to see if we know whether or not they'll dissociate from the table. So the first one we'll start off with is calcium carbonate. So does calcium carbonate dissolve in water? So you're going to sit back and you're going to look at compounds containing the following ions are soluble. Compounds containing the following ions are insoluble. All right. So I'm not seeing, for the solubility situation, compounds containing the following ions that are mostly soluble. The two ions that we have here are calcium 2+ and CO3 2-. That's for this one right here. Okay. So I don't see anything, I don't see anything on this side that indicates anything about calcium or carbonate. But what I do see down here is I see carbonate down here. And it says the following compounds are mostly insoluble. So right off the bat, I see carbonate, and I'm going to sit back and say, all right, this is probably not soluble because I see carbonate right here. But I'm just going to double check and make sure. All right, are there any exceptions to this rule? and I look over and it says, when either of these ions pairs with lithium, sodium, potassium, or ammonium, the compound is soluble. So because I have no exception, all right, this means that calcium carbonate is insoluble. All right. Let's go to the next one. We have iron carbonate, right? So this is going to be iron 2 plus and carbonate 2 minus, okay? So iron carbonate, again, I'm not seeing iron anywhere over here. We already know that we can find carbonate. That's most of the time carbonate molecule or compounds are insoluble. And are there any exceptions for iron? No, there's not. So I'm going to write insoluble right there. Next one. Now we have potassium carbonate, right? Potassium carbonate. If we were to break that up, well here, if it does break up in water, it would be 2K plus, and let's put a comma instead. 1 CO3, 2 minus. All right. We already know that carbonate anions, compounds containing those, don't tend to dissociate in water, but you'll notice up in this section right here, we have potassium. All right. Compounds containing the following ions are mostly soluble. Potassium. So we have one rule stating, right, that, because we have these two, we have one rule stating that it's not soluble, and we have one rule stating that that compound is soluble, and long story short, soluble rules trump insoluble. So even though this says carbonate compounds don't usually dissolve, the fact that it says up here, right, that potassium ions do dissolve, then we're going to say this is soluble. All right, going forward, lithium hydroxide. All right, lithium hydroxide is our next one. So let's take a look. Lithium, it turns out lithium, I see lithium right here, okay, and I see no exceptions to this rule. No exceptions. So because we have no exceptions, it doesn't even matter about the hydroxide, even though it's down here. But the problem is the exception to the hydroxide situation is when it's bound to lithium. So that's going to be soluble. Next one that we have is lead chloride. All right, so let's take a look. We've got a chloride, and then we have lead. I am scanning through this and I'm not seeing any. The first thing that I see that comes is chlorine. This tells me compounds containing chloride anions are soluble, and let's take a look at any of the exceptions. It says when any of these ions pairs with silver, mercury, or lead, the compound is insoluble. So this guy is going to be insoluble. All right, so you always have to read the exceptions. Oops. Next, we have calcium nitrate. Okay, calcium nitrate. I'm not seeing calcium anywhere, but I am. Do I find a nitrate? Nitrate anions right here. Are there any exceptions to that? Nope. So we're going to say this guy is soluble. Calcium sulfate. Next one. Sulfate. I see right here. Are there any exceptions? And it says when sulfate ions pair with calcium, strontium, barium, or lead, the compound is insoluble. So guess what? This guy is going to be insol. And then finally, we have sodium sulfate. Again, sodium here, sulfate here. So we have both the cation and the anion telling us that they are soluble. So we're going to write soluble right here. So that's how you use the solubility chart. All right, you always look at the rules you always look at the rules, and then you'll always make sure that you look at the exceptions. And you also, if you have one rule telling you that the compound is going to be insoluble, and then another rule telling you that the compound is going to be soluble, solubility always trumps, or overrules, I should say, insolubility. So okay. So solubility always trumps insolubility, all right? And then if there are exceptions, though, then like we had for, looks like this guy right here, then it's going to be insoluble. So always look at the exceptions. Know that solubility always trumps insolubility, but you're going to have to look at the cations and anions and understand essentially how to read this table. This table is going to be really important when we move forward, because we're going to start looking at precipitation reactions, and you're going to have to identify them by whether or not the product that is formed is soluble in water. We're going to stop here, and we will jump, and the next lecture I'll have my head on straight a little bit better, and we will dig into the rest of Chapter 7. Okay? Talk to you guys soon.